Hi there and welcome to the next series of lectures in control systems. So, in this lecture we are going to be talking about a little bit more detail about inertial sensors and their characterization. This is usually a topic that students in instrumentation engineering take up, but this is becoming far more relevant for people across various disciplines, because the measurement and analysis of movement, right, is now spanning across multiple fields. While initially this was treated as a purely instrumentation issue, which was mostly concerned with aircrafts and ship like navigation, ever since movement started to become of great interest in robotics, in human movement analysis for medical purposes and so on, the overall usage of these inertial sensors has become far more critical, right. So, now we have people from sports who are worried about movement analytics, people from even dance and theatre who are worried about movement, and so on and so forth. So, it is not just core engineering, it is also a lot of allied subjects as well. Which is why we are going to be looking at some characterization of inertial sensors, how they affect the computation of position and attitude. Attitude means roll, pitch and yaw angles, and why they are important. Okay. So, the story so far, we have seen various types of navigational techniques. And we specifically said that we are going to be focusing primarily on dead reckoning, right. And in the previous lecture we discussed how to numerically integrate the measurements which are coming in from the accelerometer and the gyroscope in order to compute angular position and translatory position. So, just to refresh your memory, to compute the angular position we did something like the angle at time k at the sample k is the previously computed angle at the previous time sample plus the current measurement of the angular rate at the kth sample times delta t, right. So, this was the numerical integration equation we used in order to compute angles, and we did a similar thing for positions as well. What we are going to do today is to look at accelerometer. We've already seen how to compute velocity and position. We specifically going to be looking at noise characterization. More specifically, we are going to be looking at a problem of drift, which really comes about mainly in the gyroscope thing. It is actually not part of accelerometer. The reason I put this here is it is very common mistake that people think that drift is a problem with IMUs. It is not. It is a problem which comes only with gyroscopes, not with accelerometer. Okay, so you should remember that. Similarly, we are going to look at the gyroscope, various noise characterization of that, and then what kind of conditions it has, noise characterization, and then we are finally going to conclude with a very brief description of what kind of filtering techniques we may use in order to reduce navigational errors, right. Good. So, let us go ahead. And okay, quite a few of my students have contributed to various works in navigation that have been involved over the past few years. We have run projects with hospitals and autonomous vehicles, and these people have actually contributed a lot. And specifically Vinay Sridhar, he is going to be showing some experimental results over the next few lectures. All right. So, in this lecture, well, this is what I have basically described. While you need to remember one thing, there are some extraordinarily important details of sensor characterization which we will be brushing aside really quickly without going too much into the details of that. That is actually very important. If you want to have extraordinarily good navigational precision, accuracy, you need to really worry about a lot of details. But the objective for a second or third year undergrad student is really to just have enough information to develop your own navigational system by the end of this course. All right, that is really the objective of this set of lectures. Okay, so general introduction. Right, there are various type of inertial sensors, and these basically depend on how you actually fabricate and design them. So you have mechanical, optical, MEMS, and so on. We are going to be exclusively focusing on the use of MEMS sensors in this series of lectures. I will explain this why later. The main disadvantage of mechanical sensors is they contain moving parts, right. So, there is a significant amount of wear and tear, fairly accurate, but they suffer from this problem. Optical sensors are extraordinarily accurate, okay, but they are very, very expensive. MEMS sensors are the kind of sensors that you have in your phones when you do the portrait to the landscape mode, it shifts. You also have these sensors in various drones and UAVs, small robots which you keep playing around, and so on. So, MEMS sensors are really cheap. In fact, as I have written here, you can buy a simple MEMS 3-axis accelerometer for just a couple of ₹100. And yeah, and the really important reason why they are so useful is that they are highly versatile. I can actually just take a MEMS sensor off the market and directly interface it to my accelerometer and start to work with that. To do that with optical sensors and mechanical sensors require a lot of additional electronics. The problem with MEMS sensors is that they are significantly corrupted by noise as compared to the optical or the mechanical sensors, and we will see a few of these noise characterizations. But to make sure that you still continue to use these MEMS sensors, there are really nice algorithms, or primarily we can actually call them as filters or filtering techniques, which have been developed to compensate for this noise. And two of the most commonly used techniques, one is the complementary filter, which we will be discussing in the next series of lectures, and the other one is a Kalman filter, right. Well, okay, so let us go ahead. Okay, effect of sensor noise on dead reckoning computations. So, we have seen the first order difference equation for computing the angular displacement once you measure the angular rate, right. So, this is the first order differential equation. This is actually what gets implemented in your computers. Now, it is important to remember that every sensor, not just inertial sensors, every sensor which you are actually going to use is the measurements are highly corrupted by noise. So, you can actually see this very often when you try to take your selfies. If you do it in slightly poor lighting, you get a lot of grainy images. Even if you do it in extremely good lighting conditions and you try to zoom into the camera, into the image, you start to get a lot of blurring effect and grainy images and so on. This is true for all sensors. You measure the temperature of this room by putting a very accurate digital thermometer costing hundreds and thousands of rupees. You are still not going to get the perfect temperature. There is always going to be noise. And of course, the same thing happens for inertial sensors as well. So, every measurement you make is actually a combination of two things. One is the actual dynamics which is happening. So, for example, you are measuring temperature, it is the actual temperature in the room plus the noise. Okay. So, this can be written for a gyroscope as follows. So, the measured angular velocity or the measured angular rate is basically the true angular velocity plus, and I am going to write this with a circle, I will explain why, plus noise. Okay. Now, so this is actually what you measure every time. You are never going to directly get the true angular velocity, it is always corrupted by noise. The meaning of this circle over the plus sign is some noise are additive in nature. So, you actually simply add it up. Some noise can actually be multiplicative in nature. Okay, there is various kinds of noise as well. So, what we are going to consider here is primarily the additive noise. Okay. So, the angular velocity measured by a gyroscope is a true angular velocity plus noise. That is a basic kind of equations we are going to be dealing with, or behavior. So, let us see one of the consequences of this. So, let us suppose, and we look at a very specific example of one noise parameter which is a constant bias. What is the meaning of a bias? Okay, let us again take the example of the thermometer. Let us say the temperature in this room, God or somebody has told us it is exactly 23.1 degrees centigrade, exactly, no other decimal points, 23.1. The thermometer is going to show always 23.12. Okay. So, the exact temperature in the room was 23.1 degrees. God or someone has actually told you this. Your thermometer shows 23.12. This is by the thermometer. Let us go to another room, okay, a different room where the temperature in the new room is 43 degrees and your thermometer will show 43.02. Okay. Go to another place, there will always be a offset from the actual true temperature in our particular example by 0.02 degrees Celsius. This constant offset is called a bias. Okay, is there in every sensor. So, let us see, and actually it turns out that this is one of the most dominant noise effects which you find in all sensors. So, let us see now in the next 2-3 slides what is the effect of this bias on our computations. Now, remember I am going to first start off with the example of computing the angular position by using the angular velocity measurements. So, we look at what happens to the angular position, the angles when bias is present. Let us take us even more specific example in a simulation. I will do a practical experiment later on. In a simulation, let us say the bias error, okay, or the bias is 10 power minus 3 degree per second. It means every second I have a bias of 0.001 degrees. Okay. Remember, I am measuring the angular velocity. So, every second there is this factor added. So, this factor is added every second. That is basically what you have over here. Okay. Now, let us take a even more specific example. Let us say I have this laser pointer in my hand, and think of it as a pendulum, right, which oscillates like this. Now, if it goes say from this vertical position to the horizontal one, we say that there is a 90-degree change. If it takes 1 second to go from the vertical position to the horizontal, we say that the angular velocity is 90 degrees per second. Okay. If it takes 5 seconds to go from this horizontal position to the vertical position, we would say the angular velocity is 90 divided by 5 degrees per second, right. So, that is the rate or the velocity at which it moves. Now, let us forget about motion, let us do something far simpler. Let us just keep it as is. Okay. It is perfectly stationary, it is not moving. So, the measurement which you get, we would expect the measurement to be 0 degrees per second, right. It is not moving, it is perfectly stationary. However, every measurement is corrupted by this bias value of 0.001. Okay. What would happen if I include this bias value in my numerical integration? Let us see what would happen. So, to understand that, we need two important we need an important thing which is the amount or rather the sampling rate. This is a gyroscope, a typical MEMS gyroscope. You can sample it anywhere from 50 hertz all the way, I imagine, to around 300 hertz or something. You can even do it higher, but the accuracies are not so good. What this means is that my gyroscope is throwing out, let's suppose we take 100 hertz just for the sake of discussion. It means my gyroscope is throwing out 100 samples of data every second. Okay, in 1 second I get 100 samples of data from the gyroscope. So if I take 0 to 1 second, then 2 seconds over here, I will have 100 samples of data. Okay, what do we do? So this is basically the omega, the angular velocity. What do we do with the angular velocity? We integrate it. So we basically say that theta is theta k minus, say, delta t plus angular velocity times delta t. Okay. What happens when you are integrating? Remember, you are integrating the data at 100 hertz. So you are getting 100 samples per second. Each sample is being integrated. So let us do this following example. Let us suppose the initial value of the gyro, which is perfectly at rest. Okay, theta, the angle at time 0 is 0 degrees. This is the initial condition. Now, so this is known. Now I want to compute theta at the next sample. So in this case k was equal to 0. Now let us see what happens when k equal to 1. So that is theta of 1 is nothing but the previous angle which I had, the previous angular position which I had, which was theta of 0, plus omega of 1, the current angular velocity which is measured, times delta t. Okay, whatever is the time interval you are taking, this delta t in our case will be equal to 1 over 100 hertz, because we are sampling at that rate. Okay, so we are going to look at this expression now. Okay, so what was theta of 0? That was 0. What is omega of 1? If it is a gyroscope made by God, it will show that its omega measured is exactly equal to 0, but it is not made by God. So you always have a small bias. Well, let us see what theta of 1 becomes. So theta of 1 will become 0.001. Okay, this is at k equal to 1. Now what happens at k equal to 2? At k equal to 2, theta of 2 is basically the previous angle which I have measured plus the current gyroscope value times delta t. Let us for the moment ignore the effect of delta t over here. We will just assume it to be 1 without any loss of generality. You will get the same kind of results when you take the correct delta t. Okay, so we will wrongly assume it to be equal to 1, but you get exactly the same kind of behavior even if you take the correct delta t. Okay. So theta of 2 is equal to theta of 1, which is 0.001, and again I have a bias. The true measurement is 0, but I have a bias. Again I add 0.001. All right, and this is nothing but 0.002. Let us do it one last time. So theta of 3 will be equal to theta of 2 plus omega of 3. Sorry, this should be a 2. Omega of 3 times delta t. Add it up again. So you get 0.002, the previous value, plus 0.001, and this becomes 0.003. What is happening? Every single time I am integrating the gyroscope measurement, the angular velocity, the actual angle computation, the angular displacement is drifting away. It should be exactly at 0, right, because my measurement is actually 0. There should not be any angular velocity measured, but every single time we are integrating noise, the bias value, and it is drifting away, see, 0.01, 0.02, 0.03 and so on. You simulate this. I have done this for 16,000 samples over here. So k was equal to 1 to 16,000 in my code. I will be sharing the code with you later. And you do this for 16,000 samples and you will see that the drift actually goes linearly like this. It's a perfect linear curve, whereas the true value of the angle, so this is the angular position in degrees, it should have been 0 for all time. And what is the computed angle? It drifts away like this. This is always going to happen, and a better quality sensor will reduce the amount of drift. Maybe it will be somewhere over here. A really expensive sensor may keep it somewhere over here. Otherwise, in every single case, you are never ever going to get a perfectly computed angle with your gyroscope thing. Okay, this is the phenomena of drift, and drift here basically means you are drifting away from your true angular position. Okay. Well, that is true for the gyroscope. Now, what happens for the accelerometer? And you will see it's even worse. And why? Okay, so let's assume the same kind of noise profile. So the bias is 10 power minus 3 meters per second. Again, we will wrongly just assume delta t equal to 1, but this is not really important. You need to take care of it in your actual code to make sure that delta t is actually 1 over the sample rate. Okay, that you should take care of that. In any case, you are going to get exactly the same behavior as we will show in the actual experiments. Alright, so let us take the bias error for an accelerometer again as 0.001 meter per second square, because that is what an accelerometer measures. Okay. Let us again assume this, the same condition. The laser pointer is perfectly stationary. So, what would I measure? 0, right. So, we would expect this to be 0 always. However, there is this bias which comes in. So, this is what you are actually going to measure at every instant of time. Okay. So, for all t you are going to get 0.001, and we will now see that in order to compute the angular position from the angular velocity, we had to do a single integration. For an accelerometer, to compute the translatory position, we need to do a double integration. You can already imagine what is going to happen. So, you are going to, from your accelerometer measured value, you are going to compute your velocity by a single integration. From the computed velocity, I will call it velocity computed, from the computed velocity, integrate it a second time and you get your position. Okay, which means you are, if you go to the previous slide, in every single integration, the value of this bias, the 0.001 was added one time each integration process, right. So, here we added it once, here we added it the second time, here we added that the third time. You know what is going to happen here? Well, it is going to add this bias twice, because you are double integrating the accelerometer. So, if we know from the previous slide that if you plot the velocity as a function of time, which was obtained by a single integration with the bias of 0.001, we are going to get something like this, a straight line. This is the drift, when the true velocity should have been 0, because even the acceleration is 0. Now, remember that we are double integrating the acceleration. So, it means that we take this linear drift over here, integrate it one more time, and what you are going to get is actually a parabola. Okay. Single integration results in a linear drift, double integration results in a parabolic drift. That is what we are going to see over here. So, this is a simulation which I done in MATLAB. I will happily share the code with you, and these are the two equations, for one is for the velocity, one is for the position, and you see that in the first plot over here, you see in the first plot over here, right. So, what you see is this curve is the velocity curve, which you got by single integrating the accelerometer data. This curve is actually your position, which you got by once again integrating the velocity. Okay, and you can see the error between the two because of the double integration has grown so much, right. Let us just run this simulation for a sufficiently long time. Again, all of this is synthetic data. I have created this in MATLAB software. This is not true data. The real experiment will be conducted a little bit later in the next lecture. So, let us run this for 16,000 samples, which is approximately 2 minutes and 30 seconds, where the sensor was stationary, perfectly stationary. And you can now see after 2 minutes 30 seconds, my position, which was supposed to be where 0, has now gone to almost 1.1 meters. So, it means the laser pointer, which was supposed to be here, has gone even farther away from that, more than 1.1 meters away, right, in just 2 minutes and 30 seconds, while it is really not moving. That is the effect of drift with the double integration. Okay. So, this is actually the problem with dead reckoning. You will always get drift in dead reckoning. If you remember the desert ant example which I gave before, the poor guy is actually trying to use his legs. The ant computes the number of movements of the legs in order to calculate how much distance it has travelled. Now, let us say that he is counting 1, 2, 3, 4, 5, 6, and it by mistake it forgets to count a few of the leg movements. That error now starts to add up, because there is an error, right, a small error. It may have forgotten 2 leg movements, that gets integrated every single time, like, and it is going to produce this kind of a drift. So, it may have walked 10 meters and it thinks it has walked maybe just 5 meters or 50 meters, it does not know. And it is true for all navigational processes. Okay. So, drift is bad, it is even worse in double integration. Okay. So, now before we go ahead with techniques of how to remove this drift, let us see in some detail what are the characteristics of these sensors. Let us look at the gyroscope first. Okay. The gyroscope is an interesting sensor. Let us say you have a spinning ball, okay, or a gear, as what you can see in your slide over here. Now, remember, the gyroscope is a 3-axis sensor. You can also have a single axis gyroscope, but we will be dealing only with 3 axis here. So, let us say you have a single axis gyroscope which is mounted like this, and you have a ball which is spinning, okay, spinning in a clockwise direction. Let us fix the gyroscope on the ball. So, the ball is spinning and the gyroscope obviously spins along with the ball with respect to the vertical axis. So, this picks up the rotation rate of the spinning ball, right. So, there is a small illustration over here. So, these are gears which are moving, and you put a gyroscope in that, and the gyroscope measures the rotation rate with respect to its vertical axis, and it will say maybe it is going at 10 degrees per second or whatever the actual velocity is, right. So, that is what you see. Now, the cool thing about the gyros is the following. Where is this? Yes. The cool thing about the gyros is that where if you have a sufficiently sensitive gyroscope, you can even pick up the rotation rate of Earth, right. That is really amazing. So, you are on Earth, Earth is rotating all over you. I have absolutely no, I mean, I cannot sense the rotation rate of Earth. I mean, I am sitting, everything looks static to me. You place a sufficiently sensitive gyroscope and it can actually measure the rotation rate of Earth. The problem with the rotation rate of Earth is that it is very slow. It is 15 degrees per hour. You calculate this per second, it is a really small number. And what is 15 degrees per hour? Well, let us see. So, that is 15 degrees every 3600 seconds, right. So, what is the rotation rate for every second? Well, it is 15 divided by 3600, that is approximately 0.004 degrees per second. So, this is the rotation rate of Earth. and most gyros are not sensitive enough to pick up this rotation rate, which is a good thing, because every time you pick up such rotation rates you need to now compensate for this, right. So, it acts like a bias. It is not the true motion of your vehicle, it is not the true rotation motion of a vehicle, there is also an extra component of earth rotation rate. Luckily our MEMS gyroscopes are not so accurate and they do not really pick up this thing, and one of the reasons why they do not pick up is that our noise component, okay. So, the actual bias of the sensors itself is usually much larger than the rotation rate of earth, and because of that your noise dominates the earth rotation signal and you can never actually see it in these relatively low cost MEMS gyroscopes. The other thing is, if you, and I think you need to do this thought process yourself, a thought experiment, placing the gyro at the equator, okay, pointing exactly at north will give you the rotation rate of earth. Place the same place the same gyroscope exactly at the poles, north pole or the south pole, you will not measure the rotation rate of earth, okay. I really want you to think of that experiment. Okay, good. So, that is what the MEMS gyroscope does. And well, what are the errors which we can encounter in a gyroscope? So far we have seen only the constant bias error, okay, and it was a constant offset, but there are lots of other errors. So, one which we saw was a constant bias, then you have something called the bias stability or the bias instability, both mean relatively similar things expressed differently, and what this basically means is that we always assume our bias is constant, but that is not really true. You turn on your gyroscope, a MEMS gyroscope, and you calculate and you keep it in a perfectly stationary condition, okay. So, let us say we are looking at one particular axis, it can be any axis, as a function of time in a perfectly stationary condition, okay. So, it may have maybe some noise like that, right. This is the 0 value. It may have some slight deviation from 0 over a function of time, and when you take this entire data and compute the mean of it over say about 5 minutes, you will get a particular value. So, we will call it noise 1. You turn off the gyroscope and maybe after a couple of minutes turn it back on again, okay, and then what you are going to get is a slightly different noise signal. Again it will be around 0, but it will be slightly different from the previous one, okay. And now when you compute the mean, it will be a different value, slightly different, but it will be different. You can repeat the experiment again if you like, if you are sufficiently interested or bored in life, and you compute the mean the third time, you are going to get a third. Keep repeating the experiment every single time, turn it off, turn it on, wait for 5 minutes, collect the data, calculate the mean. Every time you are going to get a different answer, which means your bias is not really stable, it is not a fixed constant bias. So, that is another problem, okay. The reason why fixed constant bias would be amazing is because you can actually, before the start of your experiment, navigation, robotic navigation, whatever, you can just turn on the gyroscope, wait for 5 minutes, calculate the mean of that, that is your offset, right. Now, every time in the future, if it is the same offset, what I can do is the following. So, W measured is W true plus the noise, right, plus the noise, and let us assume only bias, a fixed constant. If I am able to model this one, if I am able to calculate this from all my previous experiments, all I need to do is to subtract from the W measurement my bias constant offset, and I will really get my true value. This is actually a standard procedure which is called as calibration, and we do this all the time with gyroscopes or even with accelerometers. Well, it would be nice except for the fact that your bias is also time varying, your bias changes with time. It even has what is called the turn on turn off values. You turn it on, it changes, turn it off, it changes. You take the same gyroscope and you run an experiment for 1 hour. For the first 5 minutes, it will be one bias value. Maybe the next 10 minutes will be a slightly different bias value. After another half an hour, maybe another slightly different bias value. So, bias is time varying. There is also a change from turn on to the next turn on condition. Then we will see other parameters called the scale factor, misalignment and white noise. These are the 3 things which we are going to see in a little bit of detail, right. So, the fixed bias we have already seen. We have also talked about bias stability. So, while we assume the bias is perfectly constant, it can actually be changing as a function of time, right. It will not go too much away from the actual value, but it could be changing. This is the bias stability and it is a function of time. This is the assumed constant offset bias, which is not always true. Now, what is the bias measured in? Typically in degrees per hour, because degrees per second is a very small number. So, typically they measure it in degrees per hour. The bias stability is measured in degree per hour, because it is the variation of your bias. Yes, then you come to actually a very interesting noise parameter called the angle random walk, and basically what happens is every measurement of your gyroscope, as we have seen, we have the true value plus a corruption, right, the noise. The noise is a combination of your bias, your fixed bias, let us call it F bias, then you also have the time varying bias, okay, and you also have white noise. For the interested student, white noise has some very nice statistical properties. It is a zero mean process. For those who are hearing this for the first time, I encourage you to just go in Google and read a little bit about white noise. You may have seen it in your television screen when the signal goes off and you get that kind of sound, right. So, that is basically white noise. Okay. So, the interesting thing with white noise is that it corrupts your measurements, as we have seen over here, and the way in which it corrupts, it is a fairly complicated mathematical way of deriving it, but basically it corrupts it in such a way that the error grows as a function of square root of time. So, you actually say degree per square root hour, whereas for the constant bias it was degree per square root hour, it was degree per hour, right, whereas for the angle random walk is degree per square root hour. So, the basic, if you look at time and you look at the computed angle from the measured gyroscope, this would be the plot for the constant bias, and now I would like you to think on your own what would be the plot if theta varies. So, in this case theta is varying linearly with time, right, it is varying linearly with time. I want you to think and plot, and these will also be set of assignments later on for you. How would theta look if theta varies as a function of the square root of time? It is a very simple MATLAB code which you can write. Okay. Then you have something called the scale factor. The scale factor basically says the following: if the input, the real angular velocity is, let us say, 2 degree per second. In an ideal world, the sensor which measures this should also say that the output of the sensor is also 2 degree per second. What happens is, in reality you have a scale factor. So, the input is multiplied with some scaling parameter. Okay. So, and this is typically expressed as percentages. So, if you say that you have a 5% scaling error and the input is 1 degree per second, the actual measurement will show it to be 1.05. This is not a bias, it is a scale factor, alright. And then you have misalignment and cross axis sensitivity. Misalignment basically is the following. We always talk about 3 axis measurement, right. So, the forward axis, the vertical axis and the axis which completes the right angle coordinate system. Now, these axes have to be perfectly 90 degrees offset from each other. Otherwise, what is going to happen is the measurement, let us say you are rotating about this axis. Okay. So, the pitch angle. So, you are actually doing a pitch rotation over here. Now, if the axes are perfectly aligned, there will be a 0 measurement of angular velocity along this axis, right, which I am holding. You will only see angular velocity in the other 2 axes. However, because of manufacturing tolerances and errors in manufacturing, these are not perfectly orthogonal to each other. There is a slight deviation. Okay. So, when I hold this and I rotate, I do a pitch up and a pitch down, even this axis starts to measure a non-zero angular velocity. So, to see this in a little bit more detail, we would ideally want these to be perfectly orthogonal. Okay. So, this should be perfectly at 90 degrees. Let us take the 2 axis case. The same story applies for 3 axis. Now, instead suppose you manufactured it in such a way that this axis was slightly off, okay, and this axis stays, well, almost the same. Now, when you do a rotation about this axis, all right, you would expect, so we will call this x and we will call this y, x prime, y prime, this would be x and this would be y. When you rotate, okay, let us actually rotate about the other axis. So, when you rotate about say this axis, you which means that you hold this constant and you rotate about that, right. It means the angular velocity along x must be equal to 0 and the angular velocity along y must be greater than 0. However, because this axis is slightly misaligned and they are not perfectly orthogonal, so this may be like 89.5 degrees or something, you will find that omega x is not equal to 0, it is slightly larger than 0, and that is not true, right. So, this is again a noise. So, all these noise terms, they come together and they basically corrupt your measurement. True plus noise, and noise, as you can see, we have seen about 5 different types of noise terms. Each one of them affects the overall computation in a slightly different way. The most dominant one is a bias, that is the largest value, and for most applications it is generally enough to compensate for the bias. We do not need to really worry about, say, this misalignment or angle random walk, scale factor and all these things. If you can really compensate for this bias, which is not too difficult, you can really solve many applications which do not require very high precision. Okay. Fine. A similar story holds for accelerometer, except that every noise term in accelerometer gets integrated 2 times. So, we need to be a little bit more careful. Okay. Let us see what an accelerometer actually measures. We know an accelerometer measures acceleration, right. Okay. 3-axis accelerometer. I am posing a question for all of you. 3-axis accelerometer, it is perfectly stationary. Yeah, let us say I am inside a vehicle and I am holding a 3-axis accelerometer, it is not moving. The vehicle is perfectly stationary. Will this measure anything apart from noise? It will always have some noise. Let us ignore noise. Okay. Say the God has made this accelerometer, there is absolutely no noise. Does it measure any non-zero component? Well, the picture on the right, this beautiful color picture which you see over here, these two are basically the Earth's gravitational field. Okay. Every time you place an accelerometer at a perfectly leveled position, so the vertical axis is pointing directly towards the Earth's vertical axis, what you are actually going to measure is a non-zero quantity along the vertical axis. and that non-zero quantity is basically 9.8 meter per second square, your gravitational force or the gravitational acceleration. So, even if you are perfectly stationary, place an accelerometer anywhere on earth, you are going to measure Earth's gravity. Now, this would be fairly okay if Earth's gravity were constant. So, everywhere on Earth, if Earth's gravity is 9.8 meter per second square, I know that I can compensate for that unwanted measurement, because I do not really want to measure Earth's gravity. I want to measure how fast my vehicle is moving, not my vehicle motion plus Earth's gravity. I do not want to measure that. So, if it were perfectly 9.8 meter per second square, life would actually be fairly simple, because from every measurement of my accelerometer, I would simply subtract 9.8 meter per second square, okay? And then I will actually get say a much better measurement, okay, with just the noise terms being available, and this one compensated. The problem with that is that Earth's gravitational field is irregular, and you can see this picture, and surprisingly, even I did not know this, it is very fascinating to see this. India actually has extremely well, relatively speaking, India has fairly low gravitational field over here. So, all the colors in dark are where the gravitational field is much are large, and the blue colors, so the bright red colors is where the field is very large, and the blue color is where the gravitational field is really low. And interestingly, India and literally where I am sitting right now in Chennai, the gravitational field is really low. So, it will be less than our expected 9.8 meter per second square. So, now this is another problem, right? You need to compensate for this, but you cannot do it directly unless you have this Earth's gravitational field data with you, right? So, really professional navigators, they always they compute the latitude, longitude, altitude of where you are on Earth, all right, and then they subtract out the corresponding gravitational acceleration from that particular place, okay. Right, but otherwise basically if you ignore all of this, an accelerometer basically measures the acceleration, and it will always measure the Earth's acceleration as well. Here also what we discussed before with the gyroscope, the misalignment becomes very important. So, if the axes were perfectly aligned, so this vertical axis, well, let me redraw that bit nicely. Okay, so let us say you have a vertical axis and the other two axes over here. So, this vertical axis would measure 9.8 meter per second square. If it were perfectly vertical, it is never the case because of manufacturing defects. So, maybe it is something like this. Okay. Now, this would be the real vertical axis. Now, because all the three axes are now slightly misaligned, okay, whereas this should have been 0 meter per second square, the other axis should also have been 0 meter per second square. Now, each of the axes will measure a quantity greater than 0 meter per second square, and of course, the vertical one will be the largest, depending on how much misalignment has happened, it may be 9.75 meter per second square or whatever. This is a problem of misalignment. All the axes start to get corrupted by values which they should not be measuring. So, the same thing with the accelerometers as well. You have a fixed bias, you are doing a double integration, and the drift grows really large, and we have seen that it grows linearly with single integration, and the position it grows as a quadratic term, okay, that parabolic shape. The bias stability is similar to the angle random walk. The behavior is very similar, and the drift, when you do the single integration, it grows as a power of t 3/2. You do a double integration, it grows as 5/2. Okay, whereas the other one was linear and quadratic. This grows at these rates. We will not really go into these two details, except to say that the bandwidth of a sensor, and not just accelerometer, even for gyroscope, is extremely important. If you have, let us take my arm, let us say the arm is moving at a rate of 1 hertz, right. It means I am able to do this motion in a 1 hertz cycle, which means it takes me 1 second to do this motion, 1 second, 2 seconds, 3 seconds and so on. If this is the motion which I always expect, there is absolutely no need for me to use a very high bandwidth gyroscope or accelerometer, right. There is no need for me to use like a 1000 hertz bandwidth accelerometer, because I do not do anything with all the remaining frequencies. It is really just the 1 hertz component which I am interested in. If I am a missile and I am moving extremely fast, right, I do not know how fast these missiles actually change their paths, but you could really be looking at fairly high frequency of say 50 hertz or something like that. If you have these these cantilever beams which are attached to walls and you tap on them and you have these vibratory motion, these can go really very high frequencies, and for that you would use a different accelerometer as well, right. So, the bandwidth is an important property. Finally, while I will not spend too much time on these, it is important for everyone to realize this. The input range, basically what I have just been talking to you, the input range is very important. For high speed dynamic motion you would require a high bandwidth gyroscope or accelerometer. For a low speed or low dynamics motion you would require a low bandwidth accelerometer or a gyroscope, and the range actually determines that. Okay. Accuracy of course is important. The more accurate your sensor is, the more expensive it is, but the more better it is. Resolution and sensitivity again are important. Sensitivity basically says it is defined as a ratio of the change in the input to the actual measured value, right. Sorry, it is defined as a change in the input to the change in the output signal. So, if you take let us say your sensor over here, let us say we give it an acceleration or we give it a angular velocity. Okay. For a delta change in the acceleration, means for a very small change in the acceleration, if there is a corresponding change in the voltage or in the response over here, okay, that is very good. It means that we can measure really small accelerations. However, if it takes a large input to have some amount of data coming in over here, then it means our accelerometer or gyroscope are not sensitive enough. All right, that is a basic meaning. We will ignore this nonlinearity, you can look up in the data sheets. We expect behaviors of sensors to be fairly linear around certain operating regions. In real life, as we have seen in the previous lectures, they can be slightly nonlinear, not as much as I have drawn, but slightly nonlinear. Okay. So, all these effects start to become important when you really start to worry about accuracy. If you are comfortable that your application should have reasonable accuracy, and reasonable accuracy is what you should define for most home automation or even most robotics application. I mean, a MEMS sensor is good enough, and even more specifically, you do not need to really compute angle random walk, you do not need to worry about misalignment and so on and so forth, unless you want your robot which travels for say 2 kilometers to know exactly where it is with very high degree of precision. If you are not too worried about that, focus on the constant bias, remove that through a calibration process which we will be showing you in the experiments, and you are pretty much done. Okay. So, this is accelerometer data sheet from Analog Electronics, and there is quite some interesting information which they provide in the data sheet. So, you can see that the bias value is fairly high, it is about 150 milligram, 150 mg. The g basically 1 g would basically be 9.8 meter per second square. This is actually the acceleration I am experiencing right now without any motion. If I add an extra motion, it is 9.8 added to that extra acceleration which my body will be providing. At stationary position, it is 9.8 meter per second square. Okay. And as you can see, the bias is 150 mg, that is fairly large, which is why it is important to compensate for that. Yes, so we are almost towards the end of this lecture, and what we have seen is that MEM sensors are fairly cheap. For a few hundred rupees you can buy accelerometers and gyroscope. In fact, I encourage you to go ahead and buy these sensors, because two of these sensors cost the same as two ridiculously overpriced cappuccinos, or I do not know what you guys have in these fancy coffee shops, right. So, a complete IMU with the accelerometer, gyroscope, and something called a magnetometer, is like a compass. Complete IMU costs less than 2 cappuccinos. Well, there are various techniques which we will be seeing in the next lecture on how to compensate for these noise problems. Finally, if you are really desperate and you want incredibly good accuracy, maybe you are an engineer working in aircrafts or in missile development, or even in autonomous land vehicles or air vehicles, where precision accuracy is extraordinarily important for whatever reason that you have, you would really try to go in for optical sensors. Okay. They are of course very expensive. You may need to sell your house or car to buy one of these sensors, but that is how it goes. The more expensive, the better the accuracy. The final slide is applications of inertial sensors. I will not spend too much time on this, except to point out that as the bias stability drops, as the bias stability keeps reducing, as the scale factor stability keeps reducing, meaning that the scale factor is less and less of a problem, you can do far more complex navigation problems. You can solve far more complex navigation problems. So, you can look at missiles, and you can look at submarine navigations and so on. If you have poor bias stability and poor scale factor stability, you are really looking at consumer electronics like the accelerometer which are present in your cell phones. Same with the gyroscope. The poor bias stabilities will mean you are looking at consumer type. The really low noise profile will be your submarine navigation, missile navigation, and so on. Okay. And these two graphs are taken from this excellent reference which is shown over here. Okay. So, the point of this entire discussion was that we tried to look at accelerometers and gyroscope say noise characterization, while there are plenty of noise parameters which must be considered for really serious navigation. For most consumer type of navigation, it is enough to focus primarily on the bias, okay, the constant bias, and where these noise characteristics affect your navigation is in the phenomena of drift. Okay. Solve drift, reduce drift as much as you can, focus on what is that? Focus on constant bias for all consumer type applications, not for medical, not for military and all, and for say medical and other kind of say military kind of applications, you would need to look at all the different noise profiles. Okay. This becomes very important. So, thank you very much. In the next set of slides, we will actually move on to filtering to see how we can reduce navigational errors. Specifically, we will be looking at the example of complementary filter. We will conclude that with a set of experiments. Thank you very much.